Let's solve a problem on a closed system using a closed system energy balance. There's actually two parts to this problem, and the second part is a bit complex. But let's look at how we solve this problem. We have gas contained within a piston cylinder assembly. It initially has a volume of 0.1 cubic meters, and it undergoes a constant pressure expansion at 2 bar to a final volume of 0.12 cubic meters while being slowly heated through the base. The change in internal energy of the gas is 0.25 kilojoules. The piston and cylinder walls are fabricated from heat-resistant material, and the piston moves smoothly in the cylinder. The local atmospheric pressure is 1 bar. Now, the first part of this problem, part A, we will define the gas in the piston cylinder as the system. And we want to evaluate work and heat transfer, each in kilojoules. Now, in part B, we will define the piston as the system. And we want to evaluate the work done by that system and its change in potential energy, each in kilojoules. Let's lay out our storyboard. We have a piston cylinder assembly, and whenever I have a piston cylinder assembly that is undergoing a constant pressure process, I like to draw the cylinder vertically to indicate that it is a constant pressure process. And I've drawn my boundary line around the gas, indicating that for part A at least, the gas is the system, the cylinder and the piston are not part of the system. Heat transferring energy into the system is positive heat transfer, plus Q, and an expanding gas moves the piston upward, and that is defined as positive work being done by the system on its surroundings. Let's look at everything we know that was given in the problem statement. We were given that the atmospheric pressure is a bar. We know that state 1, the pressure is at 2 bar and the volume is 0.1 cubic meters. Now state 2 is the same pressure as state 1 because it's a constant pressure process. And the gas expanded to a new volume of 0.12 cubic meters. We know a few things about process 1, 2. We know, for instance, that the pressure is constant during this process. We also know that the change in internal energy of the process, the change of internal energy of the system during the process is 0.25 kilojoules. Let's draw a PV diagram to visualize this process. We know that state 1 is a pressure of 2 bar and has a volume of 0.1 cubic meters. It undergoes a constant pressure expansion to state 2, and this occurs because it is being heated. And at state 2, the pressure is still 2 bar, but the larger volume here is 0.12 cubic meters. Now, an engineering model for part A only is that this is a closed system and that the change in kinetic energy and the change in potential energy during this process are both 0. Now, it is true that the change in kinetic energy is 0 because the system has had 0 velocity at the beginning and 0 velocity at the end, so there was no change in kinetic energy. The potential energy has slightly increased because as the gas expands, the center of mass of the gas increases a small amount. But this is a very small number compared to the other values in this problem. So we will continue to make our assumption that the change in potential energy during this process is 0. And we know this is a constant pressure process. Now, let's find for part A, where the gas is the system, we want to find the work done in kilojoules. And that's going to be obvious if we look at our PV diagram. It's the area under the pressure volume curve, which is just going to be the pressure times the change in volume, since this is a rectangle. Now for part B, where the piston is defined as the system, we want to find the work done by the system, and we also want to find the change in potential energy of the system. Let's start with part A, where the gas is the system, and let's write an energy balance for a closed system. We know that the change in energy of the system during a process is the energy at the final state minus the energy at its initial state. And that is equal to the change in kinetic energy, plus the change in potential energy, plus the change in internal energy, and that is equal to the heat transfer minus the work. Now in closed systems, generally, and certainly in case A here, delta KE and delta PE will be assumed to be 0. And so we can simplify this expression to that the change of energy in the system is equal to E2 minus E1, and that's equal to delta U, and that's also equal to Q minus W. We'll simplify this further, and we'll simply say, since the kinetic and potential energy changes are 0, we can say that the change of the internal energy in a system is simply Q minus W, where Q is the amount of energy added to the system by heat transfer, and work is the amount of energy removed from the system by mechanical work. Let's find the work for part A of this problem. And we know that the work for process 1-2 is the integral from V1 to V2 of P dV. Now previously we have evaluated this integral, and we know that for a constant pressure process, the integral reduces to the pressure times the change in volume of the system. In other words, it's the pressure during the process times the volume at the final state minus the volume at the initial state. Now we know that this process takes place at 2 bar, and that the final volume is 0.12 cubic meters. The initial volume is 0.1 cubic meter, and since we have energy or units of bar cubic meters, we need to convert that, and we know that 1 bar cubic meter is equivalent to 100 kilojoules. So we calculate that work done by the system during process 1-2 is equal to 4 kilojoules. We can now use the first law to find the heat transfer. The first law was stated as the change in internal energy is simply equal to Q minus W. Let's rearrange this since we're looking for the heat transfer. We can say that Q, the heat transfer, is equal to delta U plus W. Well, delta U was given as 0.25 kilojoules, and we just calculated that the work done by the system was a positive 4 kilojoules. So the heat transfer, and that is the amount of energy introduced into the system by heat transfer, is 4.25 kilojoules. Let's continue to the second part of the problem when the piston, and not the gas, is the system. So I've illustrated that here. I've drawn my boundary line around the piston. So the piston and only the piston is defined as our system. And we know that as the gas expands, the piston is going to move upward. Now we know that the atmospheric pressure is pushing down on the piston, and the pressure of the gas inside the cylinder is pushing up on the piston. And so there is a force equivalent to the atmospheric pressure times the area of the piston pushing down. And there's a force equivalent to the gas pressure times the area of the piston pushing up. All right. Now, the work done by this system can be calculated by integrating the sum of these forces, F dx, acting on the system. Recognize that the cylinder gas is doing work on the system. So work associated with the cylinder gas is going to be negative, while the system is doing work on the surroundings. So the work associated with the atmospheric pressure is positive. And once again, force is simply pressure times area. So let's start our calculation of the work done by this system during this process. It is going to be the integral from position x1 to final position x2 times the force acting on the system, and there are two of them, times dx. And that is equal to the integral from x1 to x2 of one of the forces is the pressure of the atmosphere times the area, and we said that would be a positive term. The second force is the pressure of the gas times the area of the piston, and we said previously that that would be a negative term, all times dx. So now what we have is the integral from x1 to x2 of the pressure of the atmosphere minus the pressure of the gas times the area of the piston times dx. But let's note that ADX is dV. So we can write a new integral. The work is the integral of from V1 to V2 of the pressure of the atmosphere minus the pressure of the gas dV. Okay, and since the pressure of the atmosphere and the pressure of the gas are both constants, we can take them outside our integral, and we end up with P atmosphere minus P gas times the integral of V1, it's the integral from V1 to V2 of dV. Integrating, we're going to get work of the done by the system during this process is P atmosphere minus P gas times V2 minus V1. Now that we've calculated an equation for work done by the system, we have values that the pressure of the gas during this process is 2 bar. The pressure of the atmosphere is 1 bar. The final volume is 0.12 cubic meters, and the initial volume is 0.1 cubic meters. So we can substitute these into the expression that we derived for work done by the system during this process, the system being the piston. It's the pressure of the atmosphere is 1 bar minus the pressure of the gas, which is 2 bar, times the final volume, which is 0.12 cubic meters, minus the initial volume of 0.1 cubic meters. And again, we'll convert bar cubic meters to kilojoules. And we calculate that work done by the system during the process is a minus 2 kilojoules. Now, since the work is negative, work was actually done on the system, not by the system. In other words, work added energy to the system, and remember, the system is the piston. So energy was added to the piston by work. Now we want to find the change in potential energy of the system, which is the piston. We'll do that through an energy balance. We'll say that for a closed system, the change in the change of kinetic energy plus the change in potential energy plus the change in internal energy is equal to Q minus W. Well, let's look at some of these terms. Delta KE is the change in kinetic energy, and that is 0 because the piston was at rest in both state 1 and state 2, so there's no kinetic energy change to consider. Q is 0. There's no heat transfer to or from the piston, okay? And also delta U is 0 because without heat transfer, there's no change in the temperature of the piston. And internal energy can only change if the temperature changes. So we'll have the first law of thermodynamics for this closed system now reduces to simply delta PE is equal to minus W. So let's insert our values. Delta PE is minus the work done by the system, which we calculated to be a minus 2 kilojoules. Therefore, the change in potential energy of the system, that is the piston, is equal to 2 kilojoules. Now, if you think about it, this makes sense. Since the work done by the system is a minus 2 kilojoules, that means that 2 kilojoules of energy was added to the system by work, which raised its potential energy by 2 kilojoules. Hope that makes sense to you.